Alright, so we're going to do another couple example problems, as I said, with some of these circuits in Chapter 7. Just so you know that this is actually assessment problem. I was basically going to abbreviate assessment here for a second with 3 letters, and then I decided not to. If you think of abbreviating assessment with 3 letters, you can see what I would have gotten. And this is actually on page 240. So this is again giving us more practice with these RC and RL circuits. This is a multi-switch problem, which we've done one before, but honestly I think if you can understand the multi-switch problems, the single switch ones are quite frankly the same, just easier because there's fewer steps that we have to employ. And actually I should mention this is a 10 milliamp circuit. So the problem states that switch 1 here has been closed for a long time and then opens at t equals 0. And we're supposed to find, part A, we're supposed to find V at t for zero greater than or equal to t less than or equal to 0.01 seconds. But remember, 0.01 seconds is 10 milliseconds. So basically we're supposed to find V at t until this switch closes. So first off, since the switch has been closed for a long time, let's look at that circuit. So I'm going to be kind of going back and forth on this, unfortunately. That's the only way I can do it. So I'm just going to draw the circuit that we have here with the switch being closed for a long time. And actually I'm going to redo this capacitor because this is an open circuit, because capacitor behaves as an open when it's been charged up. And of course we're doing this because we want to find VC at 0 minus, because we know again that voltage for a capacitor stays constant when you open or close the switch. And so this is 40K, this is 60K, and then this is 25K. Now, what we would do here is we of course need to find V out, but one thing we can do is do a source transformation. And doing a source transformation, I'm just going to erase it here and redraw it. This 40K would go in series, and then we'd have a voltage source here, and so this would be 40K, and the voltage source would be 40K times 10 milliamps, which if I do my computations correctly, that should be 400 volts. I'm just double checking. I was trying to download something in the background and obviously it just jumped on the screen here. So I'm just double checking here. 40K times 10 milliamps. Yeah, 400 volts. Great. Alright, so then we have to figure out what the actual V out is. Now, you could do all sorts of analysis here, but honestly, the easiest thing to notice is just doing a simple voltage division, because these two are in series, so if we combine these two resistors together, I'm just going to kind of do that. That's, of course, 100K. And then we just have a simple voltage division to get what the VC at 0 minus is, because that's in parallel with this 25K ohm resistor. So this should be 400 volts. So we'd have that VC at 0 minus is going to be 25K over 125K, because I just add all the resistors up, times 400, which I believe is 80 volts. And I'm just double checking on my calculator here. Yes, 80 volts. Alright, so then that gets me what VC at 0 plus is. 80 volts. Alright, now I'm going to redraw the circuit with that switch being open. And now the other switch isn't closed yet because this is from 0 to 0.01 seconds. So I open that switch now. And this is the circuit I would have now. And this is 60K, 25K, and this is 1 microfarad. Alright. So we can also figure out what V final is. V final, well, that's just going to be 0 volts. How do I know it's 0 volts? Well, in this situation, there's no power supply here, so the capacitor is eventually going to dump all of its charge onto that 25k ohm resistor. Now, I want to point out something here. This 60k ohm resistor, it's actually not really present in the circuit. This really simplifies to the circuit right here. Now, let's think for a second why that would be the case. Well, thinking about current here, current can clearly flow through the 25k ohm resistor, you know, because I've got a loop here. But if I try and have current flowing through the 60k ohm resistor, I end up having this open circuit over here. So this 60k ohm resistor basically is not really attached to the circuit. I mean, one end of it's attached to the circuit, but the other end is attached to nothing. So you could imagine this being just in the air. So since it's not attached to anything, that really doesn't become part of the circuit. Alright, well then, same kind of game here. We find tau, and in this case tau is easy because it's just a simple 25k times 1 microfarad, which would get you 25 milliseconds. And now we're ready to write my equation down, because remember, we have, for capacitors, we're looking at voltage, and so it's V final plus V initial minus V final e to the negative t over tau. This is really the only equation, this along with the current one for inductors, that you really need to know to solve these problems, because you can always find the final value. In this case it's 0, so we'd have 0 plus 80 minus 0 e to the negative t over 25 milliseconds, which would give us 80 e to the negative t over 25 milliseconds. And then this would be volts. Now, if you look at the answer in the book, it doesn't have this in the book. What the book has instead is 80 e to the negative 40t volts. And all they've done is they've just done that 1 over 25 milliseconds is equal to 40. That's all they've done there. Either one of these would be acceptable as an answer. So either one of these you could write as an answer. That would be fine. Alright, so that's our answer for part A. So part B is wanting to know V out at t for t greater than or equal to 0.01 seconds. Now, we need to find the initial voltage, so we need to find V out at, I'm going to say, 10 milliseconds minus, because it's not 0 minus, it's 10 milliseconds minus. And remember, we did a problem like this in class before. What you need to do is actually use the equation that you got in the first part to determine what that would be. And then you just do this computation. So let me do that computation quickly. And rounding it to 1 decimal point, you get that this is equal to 53, I'll do it to 2 decimal points, 53.63 volts. So this is my initial value. And so then I also know that the initial value at 10 milliseconds plus is 53.63 volts. Now let's look at what the circuit is. The circuit we have here, when that switch closes, let's draw the circuit. Now, we can still ignore this 60k ohm resistor. That's still not doing anything here. But then we have here $25K, 1 microfarad, 100K. And again, here V final is easy as well. V final is still going to be 0 volts. But the difference here is that the time constant is not going to be the same. Because my time constant, remember, tau is equal to R, really it's R equivalent. Actually, it's R equivalent times C equivalent is really what it is. But in this case, my C equivalent is 1 microfarad because there's just a single capacitor there. But my R equivalent is 25K in parallel with 100K. So if I do 25 times 100 over 125, what do we get here? You get 20 kiloohms. Come on. There we go. So we get 20 kiloohms. So that means my tau is going to be 1 microfarad times 20 kiloohms. So instead of 25 milliseconds, it's going to be 20 milliseconds for my tau. So then for t greater than or equal to 0.01, we would have that my V out at t is equal to, well, my final value is 0 plus my initial value, which is 53.63 minus my final value, which is 0, e to the negative t over 20 milliseconds. And of course, you don't really have to write this step down. You could really just write the answer down because the zeros clearly just do nothing, and so really the answer is just 53.63 e to the minus t over 20 milliseconds. Volts. And again, the book, when you look at the answer here, is slightly different because they wrote this as, oops, and actually I have a mistake here. I always forget to do this. Very easy thing to forget to do, and I always forget it, so I'm demonstrating a mistake you shouldn't make on the exam. When you're doing it at a different time, because we're now doing it at 0.01 is where we're starting. We have to do t minus 0.01. Very easy thing to forget to do, which I clearly demonstrated how easy it is to do. Now, as I was saying earlier, the book has this at negative 50 times t minus 0.01. And that's just because, again, they did the 1 over 20 milliseconds to get that. All right. And I'm going to ignore doing part C and D on this because I'm not really going to focus on that in the exam, because actually the way you have to do these, I'll show you how you have to do these here, is that we have omega is equal to, 1/2 CV squared, but this is for time t. So that's for one specific time. In order to actually get the total power or total energy dissipated, you actually have to do an integral. So like for instance, if you want to talk about the energy dissipated for the first 10 milliseconds, it would be the integral from 0 to 0.01 times the power. So you'd have to figure out what the power is by finding the current, things like that. And then you'd have to integrate that from 0 to 0.01, which basically I just don't want to have to take the time to do that. So we're going to ignore actually doing that. And so that would be the end of this problem here.